Time now, 11 o'clock here in Baton Rouge. And what time is it in England?
It's 5 o'clock.
5 p.m. Okay, so we've had 3 lectures in a row this morning. One at 9, 10, and 11, but for those 3 countries, it was 5, 5, and 5. Now, so you remember 3. Well, anyway, our next speaker is Ricardo Palomino from the University of Manchester. And his talk is Relative Quantifier Elimination for Lattice-Ordered Modules of Continuous Semi-Algebraic Functions on a Curve. And maybe I should show you the audience here that you're speaking to. You've already seen them a little bit in one of these windows of your Zoom.
You can see Mark is waving, yes, and Professor Madden also, yes, yeah, all good. Excellent. Right. Thank you very much for the introduction, and also thank you very much to Professors Delzell and Madden to give me the opportunity to give this talk in this great conference. There's been many great talks, and it's a pleasure to be here, even though it is remotely. So the things that I'm going to talk about today are part of my work on the PhD thesis that I've been doing under the supervision of Marcus, and that I will submit at some point by the end of this year. And so more or less the plan of the talk is the following. So this is going to be a talk on intersection or using model theoretic techniques to study the first order properties of this lattice ordered module of continuous semi-algebraic functions on a curve. So the first part of the talk is going to be about this kind of result that was proven by Fuxin, Shen, and Weispfenning on an unpublished note that essentially says that whenever you have an abelian lattice-ordered group of functions, you can reduce or you can translate all first-order properties of such structures to the properties of their lattice of zero sets. And then in the second part of the talk, I will explain how you can use the same techniques and ideas with some modifications to give a similar result for this class of lattice-ordered modules. So please let me stop me whenever there's any question or if there's any problem with the internet connection. So without further ado, let's get us started. I know that there's experts in model theory in the audience as well as non-experts. So whenever there is going to be any technical model theoretic statement, I will also try to give a more intuitive understanding of it, just in plain English. So okay, so how do we start? Let me just start with this convention that all my groups here, all my lattice-ordered groups are going to be abelian. So what I will do is now I'll fix some notation that I will use throughout my talk. So I start with G, an L group of functions, abelian L group of functions from some set X to some O group or totally ordered group N, and I pick some element F in my L group. So I will define the zero set in the obvious way, but I also will define this positivity set also in an analogous way. One thing that we all know is that any zero set can be expressed as the intersection of 2 positivity sets. And moreover, any such positivity set is actually also a zero set, where this meet operation is the meet operation on my L group G. Okay, so now what I can do is the obvious thing. I can collect all such zero sets or positivity sets. And we all very well know that under set theoretic union and intersection, such zero sets form a lattice. It's a distributive lattice that moreover has a top element given by the zero set of the zero element in our group. And this lattice is going to have like a bottom element, I think, if and only if your group has a strong order unit. Great. So we have an L group, we have a lattice of zero sets, and I will now also introduce kind of the main first order languages that I will be working with. So I have here the language of groups. I have also the language of lattice ordered groups. And then I will also have here the language of lattices, in which I will formalize this lattice of zero sets as a model theoretic structure. Okay, I've done nothing here. So the main definition in this slide is that of a standard structure. So what is the idea here? So I start with an L group of functions G. And what I want to do is I want to enrich it with its lattice of zero sets, right? So I consider this 2-sorted structure, where in one sort I will have this group G, which I'll regard as a structure in this language of L groups in the obvious way. Then we'll have another sort for the lattice of zero sets of this group, which I will regard as a structure in this language over here. And then I will connect these two sorts with this positivity map that sends each element of my group to this positivity set, right? So so you can just think maybe of this somehow as if you're giving an L group of functions. I'm thinking of this lattice of zero sets as a kind of space of values in a way analogous to that of the value group of a valued field. And then the positivity map is kind of playing the role somehow of the valuation, more or less. Yeah. So okay, so we have this. The standard structure is just going to be an abelian L group of functions enriched with its lattice of zero set, and this is a perfectly valid mathematical structure. But moreover, it's also a model theoretic structure, right? So you can formalize this within first order model theory in the way that I've done in this definition. Good. So before I give this Shen and Weispfenning theorem, I need to give an extra ingredient, and that is going to be the patching condition. Okay, so what is this? Once again, I start as before. I have an abelian L group of functions, and I say that this is closed under patching if the following condition holds. Whenever I have two elements, f and g, in my L group, and I have two zero sets A and B, whenever f and g are compatible over A and B, just meaning that f and g look the same on the intersection of A and B, then I can find some h in my group such that h looks like f on A and h looks like b on g, right? So somehow, whenever I have two functions f and g which are compatible over A and B, I can glue them together into a function inside my group in the way that you see here, okay? Right? So this is just a property of this L group of functions. But the interesting thing is that one can formalize this property in a first order way in the canonical standard structure of the L group. So the formula is not very nice, but the point is that the property of this structure of this L group being closed under patching is first order expressible inside this standard structure. Okay, great, that's a definition, but it might not be enlightening. So let's see a very concrete example of when this patching condition is satisfied. Okay, so this example comes from real algebraic geometry or minimality. So if I fix now n to be a real closed field, x to be a closed and semi-algebraic subset, and now I consider G to be the L group of all continuous semi-algebraic functions on X. And my claim is that this L group is closed under patching. Okay, so let's verify this. So what I have to do is I'm given like two functions f and g and two zero sets A and B, and I assume that they're compatible in this sense. Okay, so I want to patch this thing together, and the first obvious thing that one can do is consider the following. So I define this map H0 to be a map from the union of A and B to N, and I just define this map H0 to be equal to F on A and to be equal to G on B. And this makes sense because the compatibility condition. Moreover, this is, of course, a continuous and semi-algebraic function from A union B to N. Okay, so I'm very close to satisfying the patching condition, but not quite, because in the patching condition, I want my function H that patches F and G to be a function on my group. And this function over here is not a function from X to N. It's just a function from A union B to N. Right? So somehow I want to extend this to a function on H, but one can do this due to this semi-algebraic Tits extension theorem, which we have available in this minimal context. So by the semi-algebraic Tits extension theorem, I can find some continuous and semi-algebraic function H, so an element on my group, such that when I restrict H to the domain of H0, I look like H0. Excellent. And now one can verify that any such H that extends H0 verifies the patching condition for G. Okay, great. So that's an example of an L group which is closed under patching. So let me maybe just say that that actually somehow everything that I've said so far about L groups are about L groups of functions. So it's very well known that abelian L groups are representable. So these are subdirect products of totally ordered groups. And using this representation, one can actually see that every abelian L group is isomorphic to an L group of functions. And one can also use the same reasoning to show that when I'm given an arbitrary L group, that might be represented or not as an L group of functions, you can always extend it, you can always enrich it to a standard structure which is closed under patching. And this comes from the fact that you can represent any abelian L group as the L group of global sections of certain sheaf of L groups. Okay, good. So now I have all the ingredients necessary to give this Shen-Weispfenning theorem, which is on the next slide. Good. So what is this theorem? It says the following. So let me just break it down quickly or carefully. So what is this? What is the setup? So we have an abelian L group of functions, and we can consider it as a standard structure in the way that we've seen. So we have now a model theoretic structure, the standard structure, and I can consider properties of this structure, in particular formulas, right? So I pick an arbitrary formula, phi, in the language of standard structures, and where I'm thinking of this x bar as being free variables on the L group sort, this psi bar as free variables in the lattice or space sort. And what this theorem is saying is that whenever I have such a formula phi, then I can effectively translate it in every divisible standard structure, which is closed under patching, to a formula of this horrible form. Where, what is this horrible form? It's just a formula where you have a block of existential quantifiers over the lattice or space sort. Then I have a formula which is purely a lattice formula. So this is a formula that is telling you properties about the lattice of zero sets of the L group. And then you have a conjunct kind of relating space variables and group variables. Okay, so the kind of moral of the story is that whenever I'm given an abelian L group of functions, which is divisible, and then it's closed under patching, in such a group of functions, I can translate every first order property of the L group into a property of this form. And properties of this form are essentially properties about the lattice of zero sets. So morally, what this statement is saying is that if you have divisibles, any lattice order abelian group which is divisible and which is closed under patching, then every property of such group can be translated into a property of its lattice of zero sets in an effective way. Okay, so maybe let's see a very particular example of this in action, just to make sure that this kind of makes sense. So let this triple be a standard structure, right? So this is an abelian L group of functions. This is its lattice of zero sets, and I pick now two elements f and g in my group. Okay, so now I can one of the simplest formulas that I can think about is the following, just saying that f is less than or equal than g, and I want to translate it into a formula that looks like this. That's the goal, just to as a sanity check. Okay, so I have f less than or equal than g. Well, this holds whenever for each x in my domain, f of x is less than or equal than g of x. But if you think about it, the only thing that's saying, that statement, is equivalent to saying that this positivity set is just the top element in my lattice of zero sets, right? And this is something that I can express in this standard structure. Okay, and now you do some syntactic manipulation, and you see that this property is just equivalent to this formula over here, which is exactly a formula of the form that you see here in the theorem. So somehow the sanity check for this particular easy formula kind of makes sense, right? Good. So maybe I will just give the general proof idea. The general proof idea is essentially a lot of yoga with formulas, right? So you want to show that, okay, there's two things to show. The first one is that such formulas are essentially all the formulas in standard structures, in the language of standard structures, which don't have any quantifiers over the group, over the over the lattice L group sort. So again, here I can start with an arbitrary formula, which can be, for instance, a formula just about the L group. And this formula may have quantifiers over the L group. But this theorem is stating that even if you have quantifiers of the over the L group sort, the equivalent formula will not have any quantifiers over the L group sort. So the statement can also be translated by saying that in every divisible standard structure closed under patching, every formula is equivalent to 1 without quantifiers over the L group sort. Good. So the general proof idea is to show that essentially you're given a general formula, and you want to show that you can eliminate the quantifiers over the L group sort. Okay, so you do the usual thing of showing that actually suffices to eliminating L group quantifiers in formulas of very simple form, like the formula that you see here over in the slide. So in this reduction, I'm really using the fact, in a very important way, the fact that our L group is divisible. Yeah, here in this reduction step, divisibility is crucial. And once we know that it suffices to eliminate group quantifiers in formulas of simple form, then you just have to use the patching condition to eliminate these formulas in this particularly simple form. So for instance, eliminating this quantifier in divisible standard structure closed under patching, this formula is equivalent to this one over here, which doesn't have any quantifiers over the L group sort. Yeah. So the patching condition allows you to eliminate quantifiers, and divisibility allows you to make this reduction process. Good. So one of the main reasons why we will care about this statement is the following. The statement allows you to give decidability results about abelian L groups. In particular, if I pick now any abelian L group of functions, which is divisible again and closed under patching, then by this theorem, it follows that if the lattice of zero sets is decidable, by which I mean that its theory is decidable, then the standard structure is also decidable, as well as the L group G, right? So if the standard structure is decidable, because the L group lives inside the standard structure, then the L group is also decidable. Okay, and what if the lattice of zero sets is decidable? Well, okay, I will give you now the sketch of the decision procedure. So I pick any sentence in the language of standard structures. So in particular, it will have no free variables whatsoever. There's no X bar if I give you a sentence. By the Shen and Weispfenning theorem, I can translate this sentence in every divisible standard structure closed under patching into a sentence of this following form. But if I start with a sentence, I have no free variables. So in particular, this conjunct over here does not appear in the equivalent formula. And so we're just left over with a complete formula which is purely on the lattice. It's a lattice formula. It's a formula about the lattice of zero sets. And because we know that the lattice of zero sets is decidable, I can decide whether this formula is true or not in the standard structure, right? So that's the idea of the decision procedure. Okay, so the upshot of this slide is just that there is a way in which you can translate first-order properties of abelian L groups of functions, of certain abelian L groups of functions, into properties of their lattice of zero sets. And moreover, one can use this translation process to give decidability results for lattice-ordered abelian groups of functions. Excellent. Good. So this is the first part of the talk. So let me just get now onto the second part, which is about my work on adapting this theorem and these results to this particular case of lattice-ordered modules. So let me just start with the setup. So I will start by fixing some real closed field R, some semi-algebraic curve X, so a one-dimensional semi-algebraic subset. And I will denote in this way the set of all continuous semi-algebraic functions from X to R. Good. So as before, I can now consider also the lattice of zero sets of functions in here. And this I will just denote by L throughout the rest of the talk. Note that every zero set of a continuous semi-algebraic function is a closed and semi-algebraic subset of X. And conversely, every such closed and semi-algebraic subset is a zero set. So this lattice, you can think of it equivalently as just the lattice of closed and semi-algebraic subsets of X. Good. So let me now put all this setup together into the same context that we've seen in the first part of the talk. So what am I doing? So of course, this has more than a structure of a set. So in particular, it is an abelian L group of functions. and I can enrich it. I can consider this as a standard structure, right? So I have here the sort for the abelian L group. I have the sort here for the lattice of zero sets. I connect both sorts with a positivity map, and this whole standard, this two sorted structure is a divisible standard structure, which moreover is closed under patching due to this semi-algebraic Tits extension theorem. So in particular, we're satisfying the hypothesis of the Shen and Weispfenning theorem. Moreover, in particular, all the first order properties of this lattice-ordered abelian group can be translated into properties of this lattice of zero sets. Good, excellent. So what is the game now? Now the game is that I want to enrich the L group sort with its canonical module structure, right? So this ring, well, the set of continuous semi-algebraic functions on X is a ring. So in particular, it is a module over itself. So now I can enrich this L group sort by adding unary function symbols that I will interpret as scalar multiplication. Yeah, so this is just I'm enriching the L group sort with a module structure. And now I want to play the same game as in Shen and Weispfenning. What happens with this? How can I run the same proof through this structure? So that's kind of the goal. So what happens? I'm adding some extra structures, so I'm expecting some things not to go as smoothly. But one thing does, which is the following. So now I'm considering, I want to consider formulas in this structure over here. And the game is to eliminate module quantifiers, module sorted quantifiers in formulas inside this structure. And actually following similar ideas to the Shen and Weispfenning proof, one can show that eliminating module quantifiers in this structure reduces down to eliminating module quantifiers in formulas of very simple form, like the one that you see here in this slide. And you see here now the difference with the previous statement is that you have certain scalars that appear in this positivity set. And these are going to kind of make things a bit more challenging, trying to adapt this Shen and Weispfenning proof. Yeah. So we want to eliminate module sorted quantifiers in formulas of this very simple form. So let's see how one can go about doing this. So I'm going to put now a lemma, and then I'm going to try to explain it in a more maybe intuitive way, right? So what is this lemma saying is the following. So I want to eliminate this module quantifier in a formula of this very particular simple form. And I want to be able to characterize when I can witness this existential quantifier. Okay, so the way that I'm thinking about this, so this formula, what is this? So this is just, well, I have here an inequality. I have another inequality. So this is really a system of inequalities that I want to solve on some zero sets, on some closed and semi-algebraic subsets, right? So this is about solving a local, a system of inequalities on zero sets. It turns out that you can solve such system of inequalities if two conditions hold. One of the conditions is purely lattice theoretical. So this is this condition A. So I can solve this system of inequalities if there's some properties of zero sets that are satisfied. It's not very important which these are, but they're properties of this lattice of zero sets. And there's another condition over here in item B, which is essentially saying that if you want to solve this system of inequalities on the zero sets A and B, it suffices to solve them locally around finitely many points. And these finitely many points are just going to be the boundary points of the zero sets of alpha and beta. So, okay, so this is the technical statement. So now the kind of maybe more intuitive way of thinking about this is what I was saying is that we have this, we want to be able to know when can we solve this system of inequalities on the zero sets A and B. And we can do this if and only if A, there's some inclusions of zero sets which hold, and note that these inclusions of zero sets, this is completely expressible in this two-sorted structure M0. You need some parameters to talk about alpha is equal to 0, for instance, or beta is equal to 0, but it's still expressible in our structure M0. But then the second item B is really talking about being able to solve this system of inequalities, not globally, but just locally around finally many points of my curve X. Okay, so the main problem in this thing in witnessing this existential quantifier is that this item A is first order expressible, but this item B a priori might not be, right? Somehow you have here this existential quantifier, there exists some epsilon, this epsilon lives in my real closed field R, and a priori I have no way of accessing this inside my my two-sorted structure M0, right? So now the idea or the goal is to be able to express item B in a first order way, right? And of course, I'm here using this word locally, and I'm talking about local properties of functions. And whenever I'm thinking about local properties of functions, I think about germs of functions. So the idea now is to enrich this two-sorted structure, this two-sorted module structure, with some information about germs of continuous semi-algebraic functions on my curve X. And that's going to be kind of the goal for the rest of the talk. And the point of doing this is that, again, I want to express this item B in a first order way. I want to do this within the framework of model theory. Good. Okay, so I need to talk now about germs of continuous semi-algebraic functions on a curve. So that's what I'm going to do, and I will just start by working on the line, on just considering continuous semi-algebraic functions on R. So I pick a point on R, and I can think we all know about the rings of germs at a point, but we also have rings of germs at we have rings of one-sided germs at a point, right? So this is the ring of one-sided germs at A, approaching it from the right is just a quotient of this ring of functions modulo this ideal, which turns out to be a prime ideal. So this over here is a domain, and okay, this is very, very well known. So again, so we're considering rings of one-sided germs on the line. And I mean, there's nothing special about approaching them from the right. You can also play the same game and approach them from the left, right? You can think about rings of germs of continuous semi-algebraic functions at A minus in an analogous way. And it turns out it's not very difficult to see that these two rings of germs are isomorphic as rings. But now the important point is that, okay, so they're isomorphic, but the crucial thing here is that they're not only domains, but they're turned out to be also valuation rings, not only valuation rings, but real closed valuation rings. So equivalently, these are convex subrings of proper convex subrings of real closed fields, or valuation rings, which are real closed in the sense of Niels Schwartz. And it's not very difficult to see that that this is actually these rings of germs are actually real closed valuation rings. One has to consider certain composite homomorphism that is given by evaluation. It's not terribly difficult to show, but the point is that these rings of one-sided germs at a line, they're all isomorphic to a real closed valuation ring. And this has particularly nice properties. And this is a valuation ring, so it has a maximal ideal, and the residue field is just going to be R. Okay, great. So now we have one-sided germs, and with this, we can talk also about just usual rings of germs at a point. So we all know that this is just given by localizing, this is given by the localization of this ring at the maximal ideal of all functions that vanish at A. And it's not terribly difficult to see that this ring of germs at a point is isomorphic to this fiber product of these rings of one-sided germs. So one way maybe of thinking about this isomorphism is the following. So if I give you a germ of continuous semi-algebraic functions on R at a point A, what is this? You can think of such a germ as a pair consisting of a germ of a germ at the left-hand side of A, a germ at the right-hand side of A, and then you want these two germs to be compatible. You want these two germs to be equal when evaluated at A. And this statement of being equal evaluated at A is captured algebraically by this fiber product, right? So that's maybe more or less the intuitive way of thinking about this isomorphism. Yeah. Good. But this is okay. So this is the case with when we're working over the line. So we care also about just general curves, and for general curves, the idea is very similar. The only difference is that, of course, we cannot talk about left and right. So now we have to talk about other things, in particular, half branches of a curve, right? So in particular, for instance, this curve that you see on the slide is every point in this curve has exactly 2 half branches, with the exception of the singular point that has exactly 4 half branches. And in a very similar way to what we've done in the case of the line, you can consider rings of germs at a half branch of a given point. And it turns out again that all such rings of germs at half branches, they turn out all to be also isomorphic to this real closed valuation ring V, right? And they're also quotients by a corresponding prime idea. Okay, and so in particular, if the usual ring of germs of semi-algebraic functions on this curve at a point, it's just going to be given by an iterated fiber product of these valuation rings, where the number of valuation rings appearing in this expression is exactly the number of half branches of this point at the curve. Okay, so the only thing maybe to take from here is that somehow we wanted to have access to rings of to germ properties of functions, and even though these properties of germs are captured in these rings of germs, somehow all the germ-wise properties are really encapsulated in this single real closed valuation ring, right? And this is exactly what we're going to add in our two-sorted structure to eliminate module quantifiers, right? So, so let's do that. And so I will put a big monster definition. The only thing that I'm doing here is the following. So I start again with this structure that I considered before, this M0. So I have here this lattice-ordered module, the lattice of 0 sets. I have the positivity map. But now I want to add this germ-wise structure, which is going to be given by this real closed valuation ring, right? And remember that this real closed valuation ring is exactly the ring of germs at a half branch of my full ring. Yeah, and the way that I connect this ring of germs with the rest of the structure is with the projection map, right? So all of this ring of germs at a half branch, they're just quotients by a prime ideal in the ring. And so you have a canonical map from the ring or the module onto this real closed valuation ring V. Okay, so this is kind of like germ. These are the germ maps somehow that take any function f to its germ at the half branch at A, at the half branch at A. Okay, and I add all such maps, and this is a very big monster structure. You have many maps in here, but it's still a perfectly valid model theoretic first order structure. Okay. Good. So I have here a quick example about how now one can eliminate module quantifiers with when we add now this structure of germs to our structure. So maybe I will go very quickly about this because I think people will have a good idea. So in this particular example, I will just take, let's say, X to be the real line. I will pick this semi-algebraic set A, and I have a scalar alpha that I will assume that satisfies the property that the boundary points of its 0 set is just a singleton, just to make things a bit easier. Yeah. So what is the game? What am I trying to do here? I have this formula over here. Yeah. That is saying something about this three-sorted structure M, and it has a quantifier over the module sort. Yeah. Okay. So this formula, I want to make it equivalent to a formula that has no quantifiers over the module sort. And here is the way that one can eliminate such quantifiers. So remember that in the previous slide, I think slide 7 or 9, whenever you have formulas of this particularly simple form, they turn out to be equivalent to first some combination of some inclusions of zero sets. So this is what this item A is saying. And then remember that there was this item B that was saying that you can solve this equation or inequality locally around certain points. And kind of what I want to claim is that this formula, which is a formula with quantifiers over the germ sort, is saying exactly this. So let me just maybe go quickly through the sketch of the proof. So I have this formula over here, and by what we saw before, this formula 1 is equivalent to first some properties about zero sets, and this is what it's saying in here, together with the statement that you can solve this property or this problem over here locally around certain points. And in this particular case, this finitely many points is just 0, and that's why I chose this this notation. Okay, so that's everything that I'm saying. I just want to be able to express the fact that this thing can be solved locally around 0. And so this statement is just saying that that alpha, this statement over here just says that alpha divides f locally around 0. And this is just a statement about this ring of germs at 0, just saying that the germ of alpha at 0 divides the germ of f at 0. And this statement over here, this is equivalent to this item B that you see over here, right? And the way that you think about this, what is this statement saying? Well, it's saying that there exists some germ at the left-hand side of 0, such that at this germ, alpha divides f. Then you have another germ that witnesses that alpha divides f at the germ. And then you have these two germs of one-sided, you have these two one-sided germs, and then you want to make them compatible so that you get a full, actual, honest germ at 0. And that's what this statement is saying. It's saying that the two germs, when evaluated, right, so when you look at them at the residue field, they are the same. And that's exactly what this last formula is saying, right? So essentially, this existential quantifier over the module sort is translated into some lattice theoretic properties of the lattice of 0 sets. But the point is that this existential quantifier over the module sort is translated into some quantifiers about the germs. And that's exactly what we wanted to do. So this is just a very small example. So let me just now go through the main theorem, which is essentially an analogous theorem to that of Shen and Weispfenning, but for this particular three-sorted structure. So the theorem is a bit maybe not easy to parse. So I will just state it and then say that what morally this is saying. So we have a formula in the language of this three-sorted structure. Then the formula is equivalent in this three-sorted structure to a formula of this horrible form, where you have here some block of existential quantifiers over the space or lattice sort. Then you have some block of existential quantifiers over the germ sort. Then you have a Boolean combination of properties about the lattice of 0 sets, properties with parameters, formulas with parameters, and also formulas about the ring of germs. And the rest are just these conjuncts that are essentially capturing the relationship between the lattice of 0 sets and the module sort. And moreover, this statement can be done effectively whenever we have the assumption that we're working over a recursive real close field. In this situation, you can check that the language of M is countable and everything is recursive. And the proof strategy also gives you an effective way of making this elimination of module quantifiers. So once again, I mean, the upshot of this morally is that if you want to consider first-order properties of the lattice-ordered module of continuous semi-algebraic functions on a semi-algebraic curve, then every such first-order property can be translated into a Boolean combination of properties of its lattice of 0 sets and properties about its ring of one-sided germs, right? So kind of somehow morally, everything that you would like to know about this lattice-ordered module can be expressed with properties of the lattice of 0 sets and properties of this ring of one-sided germs. Okay, and now just to finish off in this last 2 minutes, the main corollary of this theorem is the decidability result, right? So whenever I'm working with a recursive real close field R, then this three-sorted structure is decidable, as well as this lattice-ordered module that I'm considering is also decidable. And the proof sketch, I mean, there's many things that one has to prove in here, but by this theorem, because I'm working over a recursive real close field, and this elimination of quantifiers is recursive, I just need to check that both the lattice of zero sets and the real close ring, real close valuation ring are decidable. The lattice is decidable because, well, it's so-called kind of one-dimensional topological lattice. This is some work that Marcus has done, building upon the work of Grigorchik. And the ring of germs is also decidable. Essentially, this is work by Cherlin-Dickman. So this complete theory has a recursive axiomatization, and that gives decidability. So that's essentially everything that I wanted to say. So thank you very much for your attention.
Yes.
Could you say something about what goes wrong when you deal with two-dimensional semi-algebraic sets? I mean,
Right.
a lot go wrong.
Yes, right. Yeah, absolutely. So kind of the first problem is that you don't really have a very good somehow. I mean, the rings of germs are kind of explosive in dimension 2. So for instance, I think that Cherlin proved that whenever you have a metric space, the ring of continuous functions interprets, the ring of germs of continuous functions interprets second order arithmetic. But the point is that in dimension 2, these rings of germs are not decidable anymore. So kind of you have too many ways in which you can approach a single point. So in particular, let me just go back to this slide over here. You cannot, for instance, the ring of germs at a single point, whenever you're working on a two-dimensional semi-algebraic set, and let's say that this is not an isolated point, so we're not doing anything stupid, then this ring of germs at a point, they don't have anymore this nice description as a finite fiber product of real close valuation rings. They're more wild, right? And the theory of such rings, whenever you're working on dimension 2, is undecidable. And I think that Marcus has also some work on this. So that kind of breaks badly. So yes, that's kind of what I would be able to say.
Which special kinds of two-dimensional sets would you do?
Yeah,
That's
yeah.
just that. I mean that. So.
Sorry.
Say, one could try to use it as a black box. That you could try to use the ring of germs as a black box, but then there's still a problem, right? I mean, you would have to talk about maybe scalars where the zero set is finite. And
Right.
Zero set itself is now a curve. Then you get into this kind of, and comes in 1 minute. But I mean, it's a good point. When we need to consider the statement maybe not with a whole module, but formula by formula, you fix a scalar, fix certain scalars, then there could be horizontal dimension. But it's getting really extremely difficult.
Yeah.
This process.
I mean, kind of somehow this is something that I was thinking, like how can you extend this technique? And the kind of key point is that this ring of continuous semi-algebraic functions on a curve has this very particularly nice algebraic description of being a real closed SV ring of finite rank, whatever that means. And somehow the fact that all quotients modulo minimal prime ideals are real close valuation rings, and that moreover, all such rings are isomorphic is an extremely strong property that I'm using all throughout. And this property, for instance, you don't have anymore when you have continuous semi-algebraic functions on an arbitrary two-dimensional set, but you do have them in certain real closed SV rings of finite rank, right? I mean, that would be the way or the direction in which I would kind of go and venture into generalizing this. Yeah.
Another question? Okay, well then let's thank our speaker one more time.
Thank you.